Thank you, Fernando. So as Christoph already said, I'm gonna continue the talk and talk a bit about more about model building and modular stabilization in this particular example. So this is work that appeared on Monday, and it's in collaboration, as said already before, with Michele Ciccoli, who is in the audience, and Fernando, who is the chair of this session. So he's not going to stop me, because this is also the last talk. And Roberto Valandro. So also more details, obviously, in Michele's and Christoph's talk. So just basic thing, motivation for our work is somehow we want to get closer to a realistic string vacuum and get our hands on and see what can we construct. In particular, in this work, we wanted to look at how far can we combine at this stage already modular stabilization and local model building, particular local model building at branes at singularities. So the outline of my talk, I'm going to focus on this DP0 example, in particular, so where you have these two DP0 singularities mapped on top of each other. I'm going to talk a bit about model building there in this example. In particular, I present you a DP0 trinification model, and then I'll be talking a bit about modular stabilization and SUSY breaking in this. So let's look at the example, and let's look at the picture. So let us remind us, what do we have, as we have seen in the previous talk? Well, we have an example with H11 equal to 4, lots of complex structure moduli, which I'm not going to talk about that much. And in particular, we have two Del Pezzo singularities, or two Del Pezzo cycles, devices, two DP0 devices that are mapped on top of each other under the orientifold convolution. We have an additional DP0 divisor here, which is, so to say, the small cycle of the Calabi Yau, or the Swiss cheese hole, and then we have a large cycle. As you see indicated here, we are interested in our orientifold involution. We have O7 planes on both of these cycles, but these two cycles do not intersect. So I'm going to talk a bit about the hidden sector here, how we can cancel or get our consistency constraints satisfied. So basically, let's get started. So we have two O7 planes here, as I said. So basically cancel the D7 tadpole by putting 4 D7s, respectively the images on these two cycles. Then we see that we'll have adjoints on the large cycle, 11, none on the small cycle, and as I will say, these adjoints can be lifted, in principle, by appropriate gauge flux. That's trivial in the Calabi Yau, and you have this nice Swiss cheese volume expression with one big cycle and your small cycle and quiver cycle. So let's look at in more detail. So we have D7 branes and O7 planes on non-spin devices. So we have to switch on some non-zero gauge flux F on both of these cycles in order to have vanishing gauge invariant flux curly F. We require, we turn on B field, yeah, so this is somehow special here in this situation, in the sense that we can turn it on both devices in such a way that it cancels on both of them. However, if they would intersect, this would not necessarily be possible, or this would not be possible. So, and somehow we are in some non-generic situation here. And as I said before, these adjoints on the big cycle, they can be lifted by appropriate trivial flux. However, the SO8 gauge theory that was arising on this D7 branes would be broken then to SU4 times U1 on the big cycle. So now basically what the upshot is of this is that we have the option to have gaugino condensation on the big cycle, or we can have it not, depending on what is happening to the adjoints, respectively what flux we turn on that big cycle. So this is why I brought in brackets here that we can have a gaugino condensation on the big cycle, but we definitely have in a scenario, in a setup we've chosen where we have something on this gaugino condensation on the small cycle. However, note, because this gauge group is broken, these factors here differ slightly. as will become important later on when we talk about modular stabilization. As we choose the flux to be the opposite on the orientifold on the image plane, the D5 tadpole is automatically cancelled. In particular, we have also no flavor D7 branes, so there's no contribution to the D5 tadpole from there. Now, next thing one can check is that the NS flux H3 has no non-trivial pullback on the D7 brane volume, so there's no problem there. Then if we calculate the D3 brane charge, we find that it is minus 54. So in principle, this does not include the free-form fluxes H3 and F3, which we would need to stabilize complex structure moduli. So in principle, there's space to turn them on. Whether this is sufficient space, we don't know. However, I would like to note that there's an alternative, which we discuss in the paper, is about including a Whitney brane, and in this case, we don't get gaugino condensation on the big cycle, but this can help us, for example, to get a larger negative D3 charge. Okay, now let's look at the singularity in a sense and talk about model building. So what is special about this setup is somehow that we do not have the opportunity of introducing flavor branes in the sense of in this minimal geometric setup, and so somehow model building is limited in the sense. I mean, most models that have been developed in the sense we have been working on in previous contexts always include them, and you can build really nice models, but somehow this is not possible. But you're not stuck. That is not a no-go theorem, but you have to be a bit more clever in model building, and I would like to highlight you on this example that there is something interesting structure there, and there are even more interesting examples in higher del Pezzos that have not been explored as of now. So in particular, I'll be looking at this trinification model. So we have an SU3 cubed gauge symmetry with this meta content. In particular, if you look at it carefully, you will see that the spectrum features all standard model fields. However, there are some chiral exotics which can get masses once you break down to the standard model. How about Yukawa couplings? So if you look at the in principle, there are top and bottom Yukawa couplings perturbatively. However, lepton Yukawa couplings would not be there, but they can be generated non-perturbatively. So, however, as we have been emphasizing, for example, for a long time, when we look at just the local model, include flavor branes, etc., and look just what these toric singularities can give us for models, is that we looked at the what are the local couplings if I look at the just local geometry. However, if you include compactification effects, etc., so if you break the local isometries, then in general your SU3 times U1R isometry that you have in this case is broken, and in general you should more or less start with the most general superpotential that you can write down, and there have been arguments in the literature in the past. More recently, there's some work by Anshuman Maharana, which I'd like to highlight here from last October, as far as I remember. So let me talk a bit about, I mean, this is not yet the standard model, right? How does breaking work in this setup? So if you look carefully, there is a region that we can break down to the standard model in the sense that we can break in two stages, and we break to an intermediate scale to an SU3 color times SU2 left, SU2 right, times U1B minus L, there should be, by generating a VEF in the Higgs field, in one of the fields V1, and then at a later stage we can break down to the standard model by generating a VEF for the right-handed neutrino, as Khalil talked about, as far as I know, yesterday. So then we wanted to say, okay, it's nice to look at it, and we check that obviously this is a minimum in the given potential. However, you should have a mechanism somehow to generate this, and normally field theoretical in field theory, if you're just in pure field theory, you have you just include additional fields, right? But that's not an option here, and somehow you're limited. And you have to do a bit better, and the thing is, what you really have to utilize is radiative symmetry breaking. And what we wanted to make the point, in a sense, somehow you can identify that this can be achieved given a suitable choice of Yukawa couplings at the high scale. And thank you. And so the question, obviously, once you generate such a wave by running negative, the scalar mass is negative, is what's happening to SUSY breaking, etc. So SUSY is broken at high scale. However, so so what you really need to know is how couplings can differ in this region. And for example, in the last parallel session we had a very interesting talk by Lukas Witkowski about work with Joe and David Marsh and Markus Berg about where they actually show that in an explicit or default computation that, for example, one of these couplings could be enhanced or significantly different from in an orifold model. So, okay, let's switch gears. As my chair says, I have not much time left. So let's talk about modular stabilization a bit. So I said I don't want to say anything about complex structure modular at this stage. Just assume they are stabilized using three-form fluxes, which we can turn on in principle. So then you are left with the following effective field theory. So you know normal Kähler potential with -2 log the volume plus alpha prime correction, your meta fields here, and your singularity modulus here. And the following superpotential with your normal flux contribution, meta superpotential, and non-perturbative hidden sector gauge condensation superpotential, and your volume. Now, first thing you should check is that actually, we want to be at the singularity, right? So you should check that at the string scale we are in a minimum where our singularity moduli plus G and G. So there are two because we are H11 minus equal to 1. This is the H11 minus modulus. That this corresponds to a minimum. So what you write down in that effective field theory is the D term at that scale, and you can show that there is a minimum corresponding to both vacuum expectation values T plus and G to be 0, and particular this is depending on that you have soft masses for your meta fields to be positive. So now, given that the D terms are stabilized, you can look at the rest of the potential, and you are left with a large volume potential, the typical one, which has a minimum. However, there is an additional option that we have now on this particular setup, namely that we can turn on Fried-Witten flux on the large 4 cycle, so we generate some meta fields, and they will contribute to a D term potential of this type. So now what you have is some anomalous D term with respect to the large cycle, and then you have a normal D term and some F term contribution for the meta fields. You stabilize it, and what it effectively does is it generates you an uplifting term as usual, as has been studied in field theoretical contexts. And this can give you de Sitter or respectively Minkowski minima. Here I'm showing you one nice numerical example, in the sense that we stabilize at a volume of 4 times 10 to the 6, and with very reasonable parameters, AS, the coefficient here to be 1, W naught to be 0.2, alpha prime come out is 0.5, and G string of 0.03, and note this is very nice for gut scale like string scale. However, I mean, we started with superpotential for also for the big cycle. So in principle, you could ask, what about KKLT in this setup? And if you look carefully, if you want to stabilize a la KKLT, this in principle would be possible, but you have to always satisfy, because you have the volume to be of Swiss cheese side, that the big cycle is larger than the small cycle. However, this would require that AB is smaller than AS, so in the exponential. But this is not realized here, since we have the gauge group SO8 broken to SU4 times U1. So large volume somehow seems to be favorable here. Now let me talk 1 minute, about, so this was talked about 3 years ago, but the sequestered soft masses. So let me conclude. Basically, so we have made first steps in towards combining modular stabilization and local model building. We get the standard model spectrum, and we have the zeta large volume minima. We satisfy consistency requirements. Obviously, there has to be more progress in the sense of you have to get your local model building better under control. You might want to include flavor brains. There was a very nice paper by Iñaki and collaborators about how to include them, and maybe combine somehow some hybrid model out of these nice, really local flavor models, say on DP3 with some more minimal models. And just list some open questions, but let me stop here in 1 second in the sense that I would like to announce one thing, that we are organizing a nice workshop in Bonn in the fall. So I think the summer conferences are over. So maybe you have some spare time. It's space unification and string theory, and it's surrounded around the German Unification Day, which is on the 3rd of October. So if you have any questions, look at the website or ask me. It should be an exciting workshop. So thank you very much.
Questions, Susan? Joe?
Is it really fair to say you have a standard model spectrum, or?
No. No. I mean, this is. No, I agree. I mean, it's not fair to say. Also, I mean, there are 3 Higgses, for example, right? Even if you break to the standard model gauge group, so that's not completely understood. That's even not understood in the really local models. It's just a way of seeing that they can get towards it. I mean, it is more than saying I have got SU5 gauge theory and I've got some chiral matter, right? I mean, I have got some interactions, I've got things, and but what I think is important, or what is nice about these models, is that in principle they can get to the standard model, right? I mean, there needs to be some model building to be done, at least. I mean, that's at least my impression.
You?
Why were the flavor brains so hard to?
We are in H11 equal to 4 in a sense, so you would have intersections with a lot of, I mean, with gaugino condensation on the big side. But basically, it's a computational thing that, I mean, one needs to. And I mean, Iñaki has examples of how they're realizing it. But the problem in the example that I know of is at least it has. Correct me if I'm wrong. Something like 200 Kähler moduli.
No.
No, how many? But you have a lot of Kähler moduli in the sense that.
The one we constructed, I think, was 11, 12, I think.
Okay.
11, 12 before orientifold, so you're not.
Yeah.
It started with lower than that if you want to link it.
But.
Question? Iñaki?
In this case, you wanted a relative symmetry breaking. That I guess comes because you break the SU3 symmetry in the bulk.
Yeah.
So you have an idea of how do you want the bulk to look to have that kind of pattern?
No, not 100%. I mean, there are a lot of issues in that sense, in the sense that you really, I mean, you have to see how you want the sizes of these corrections, and as usually these come with exponential, I mean, with volume suppressions, right? I mean, so they naively you would see them to be really suppressed. I mean, it's just they might be there. I mean, in that sense, yeah, this model will be probably not very nice, but I mean, we just. I mean, it's. I think the way to study this problem in the sense is to analyze more systematically how you can do these breakings. And I mean, this is all along the question. I mean, nobody has a model in the sense for how do you get all your flavor hierarchies. I mean, people write down BEFs in the sense, right? But in principle, they can be determined dynamically by having the appropriate running. So, yeah.
It is known in field theory that Or is it not even there?
Well, even in field theory, I think it is. I mean, one needs to sit down.
What about the gravitational mass?
So the gravitational mass here is set by m Planck over the volume times W naught. So that brings me to this slide. No, this is the gravitational mass. So as you see that we are at a volume of 10 to the 6, and so W naught 0.2. So we are at a really high gravitational mass, and this is very nice in the sense as for the cosmological modular problem in this sense, in principle. So yeah, this is because the lightest modular scale says m Planck over the volume 3/2, and though it's very suppressed compared to the gravitational mass, you really want to have it.
All the superpartners are really heavy then.
So they turn out to be actually of the. So for example, if you look at the scalar masses, they will be of the same order or even further suppressed. The genome mass is scalars m3/2.
But I mean, they're still. And what is the mass scale for the lightest superpartners?
The lightest superpartner scale as m Planck over the volume squared.
Which
So
is
in this
the
sense,
TeV.
that's in the TeV range. Right? I mean, if you do naive estimates. So that's nice. But you have usually a splitting between scalars and your gauginos.
The scalars are lighter than the gauginos.
No, scalars are heavier than gauginos. Gauginos are, and A terms are the TeV scale roughly, and scalars are heavier.
Have you thought carefully about what kind of gauge theory you're going to get on the small cycle that's supposed to be giving the stabilization?
No, we in the sense that only we say we we have an SO8 gauge theory there, and it should give you gaugino optimization. But
So the 07 intersects that cycle, right?
it lies on top of it, right? So
I mean, it's on the P2, or it's
Yeah.
extended and it intersects.
yeah, so you have the P2 up here, and you have the
This
07
pure,
here.
it's pure SO8.
Pure SO8.
I want to thought I did.
Okay.
Questions? Okay, let's thank the